All right, sound check, sound check. I can hear myself. Can I see our document camera footage? Looks like it. Okay, we are good to go. You know the routine by now. Put the headphones away. And let's figure out what we are doing for today. So, yeah, a little bit earlier than the time that I scheduled, but it's not like people are just sitting there waiting for the very moment that I have scheduled to show up to the stream. People just show up whenever they do, and most people watch after the stream. And I would expect most people, at least in my country, are still in school right now. So, yeah, this is again an a stream that I had to postpone. Sorry about Sunday for those of you who were waiting for Sunday. I had some stuff going on. I still have stuff going on, but I'm going to try and sneak in an extra stream or two every week or every other week so that we can get through things a little bit faster. If I don't do it, we can still finish in time, but I would rather get this done earlier so that I can free up some time for if we want to do review. I still haven't decided if I want to do like some extra review sessions after the course is done, but that's an option. And the other option is just freeing up my time to take care of all the other things that I keep myself way too busy with. So yeah, getting this course concluded is a goal I would like to reach sooner rather than later. So for today, the plan is to introduce a new chapter, Momentum, and we are most likely going to finish it in just 2 streams. If you looked at the stream schedule, I have today, and then I have another stream scheduled for tomorrow, and then that'll be it for Momentum. It'll be a pretty quick topic if things go according to plan. And after that will be circular motion and gravitation, which I will probably start on, well, I mean, we have the regular Sunday streams, but I might also want to get a head start on that and see if I can get that topic started on Saturday. So we'll see. I'm not promising a Saturday stream, but for those of you who just have to see it live when it first drops, keep an eye out because I might put something on the schedule for Saturday. Now, without further ado, what are we going to discuss for today? So, momentum and collisions, more on the momentum side today. Collisions will be more of the focus for the next stream, which is supposed to be tomorrow. So my goals for today, let me actually check with the course plan real quick. Of course, definitions, momentum and impulse is a related term that we want to talk about, and the impulse momentum theorem, and conservation of momentum and the conditions for it, and how it differs from conservation of energy and how it relates to it, if at all. Those are going to be my primary goals for today, and of course, with the time that we have left after explaining all that, we will be looking at some practice problems. So without further ado, let's get started. Momentum. The plural of momentum, by the way, is momenta. And I make sure to mention this in my lessons now, because once upon a time I had a student, I gave him a homework question where the problem was asking for something about a comparison between the momenta of two different objects, and he didn't know what momenta was until I clarified for him that it's simply the plural of momentum. If you have more than one object with more than one momentum to consider in a problem, then you have two or more momenta, not momentums. A lot of words that end with um or on, usually have plurals where you just replace those two letters with an A. For example, here's one that really aggravates me every time people use it wrong on the internet. Phenomenon. Phenomenon is singular. Phenomena is plural. It's this phenomenon and these phenomena, not this phenomena. So if you ever see somebody saying this phenomena, go post a comment and correct them and tell them Al the tutor sends his regards. Okay, I'm joking. Don't start wars with people on the internet. But it really does aggravate me because it never occurs to people. You hear the two words, and it never occurs to people to just look it up in Google and ask, what's the difference between those two words? That's how I figured it out. I didn't learn this form of pluralization in my English class. I just picked it up through thinking about these words and being curious enough to do a Google search. But yeah, phenomenon, phenomena. You've probably heard of bacteria. That's a plural. Bacteria is the plural of bacterium. And criteria. Criteria is the plural of a criterion. And so on and so forth. So, yeah, the plural of momentum is momenta. There's your mini English lesson from the day. From the day? For the day. Great. This is why I'm not the English tutor. See, I am beating the English tutor allegations. In some ways. In other ways, not so much. Whew. Anyway, defining momentum. So, I like to think of momentum as, and I'm not sure if it was Newton who gave this definition, but I'm pretty sure some physicists defined momentum as the quantity of motion. A measure. Here's like the intuitive definition that I like for it. A measure of the amount of motion that is occurring. So if you have an object, well, let's say we have two objects actually. Actually, let's have four. Well, I'll start with two for now. So let's say two identical objects, same mass, little m. And one of them moves with velocity v1. The other one moves with velocity v2, which is much bigger. You would probably be convinced if I said that more motion is happening here as compared to here. There's more motion going on with this object as compared to this one. The amount of motion is greater when the speed is greater. That makes sense. So that's one factor that you want to consider when trying to measure something's momentum. But there's another thing we can consider. What if I introduce a third object with a greater mass, capital M, and let's say it's at a velocity of v1. Comparing this object and this object, I would say more motion is going on here because even though both objects are moving just as fast, here there's more stuff moving. So the total amount of motion depends not only on how fast things are moving, but also how much stuff is moving in the first place. So with those two factors put together, we can intuitively remember the mathematical definition of momentum. Momentum is a vector and is the scalar multiple of another vector. It's mass, a scalar, multiplied by velocity, a vector. So you get P equals mv. Why on earth is it P? Apparently, it's because the French word for momentum is, what was it, petera or something like that. So that's why the symbol for momentum is a P. Momentum is a vector. It has both magnitude and direction. So when we encounter situations later where we have to do math with momentum, we need to take that direction into consideration. When we want to add two or more momenta, or subtract as the case may be, we will need to take direction into consideration as well. We will have to do some trig from time to time, unless, we get convenient questions where there are only two possible directions, forward and backward, left and right, up and down. But for two-dimensional situations or higher, we will actually need to do the same thing that we've done with other vectors, with force especially. I think we've mostly done our vector math with force questions. So there's your simple definition of momentum in mathematical terms. It's just basic multiplication. The direction of an object's momentum is also the direction of its velocity. Now, you've probably heard, and I'm pretty sure I commented on this in the force chapter, you've probably heard that a truck that is moving at whatever speed has a hard time slowing down because it has a lot of momentum. That's why it's so hard to stop it, right? Wrong. We talked about this before. The reason a truck is hard to stop when it's moving, what carries it forward when you're trying to slow it down, is not momentum. It's something we discussed in force. It was inertia. The truck has more inertia, which makes it harder to accelerate it and decelerate it. If you are walking downhill versus uphill, the reason it's easier to walk downhill is not because your momentum is carrying you forward. It's not about momentum, it's about inertia. If momentum was the explanation for this, then you wouldn't be able to explain why a truck is difficult to get moving in the first place. If a truck is not moving, well then, by this mathematical definition, it would be starting with a velocity of 0. It would be starting with no momentum. So if this momentum logic that too many non-physicists believe in was actually true, then a stopped truck would be easy to get moving, and that's clearly not the case. So that's my little mini rant reminder about inertia versus momentum. Do not use the colloquial definition of momentum. Do not use the common layperson's definition of momentum. Please be a physicist when using momentum in your physics class at the very least. I mean, I would hope that you also just keep that practice even outside of physics class, and maybe don't be that annoying person who's always out to correct people, but, you know, when you find that somebody might be receptive to it, maybe try to correct one or two people here and there. Just don't go around policing people, because they usually don't respond too well to that. Anyway, what do we want to discuss next? So I guess we could, let's do a quick example, actually. This is going to be really simple, and some of you might not even see the point in doing it, but let's do it just for the sake of checking it off. Let me find the question in the book. It gives us, I think, 4 different objects to compare. Oh, and I forgot to mention, the type of momentum that we are talking about today is called linear momentum. That's another thing I should emphasize. We're going to learn about a different kind of momentum in a later chapter called angular momentum, which is more about rotating objects. But linear momentum is about objects in translation, objects that are simply moving in straight lines. And maybe they bounce and change direction, but after that direction change, they still move in a straight line afterwards. They just switch from moving in one straight line to some other straight line. So that is why it's called linear momentum. Anyway, where was that question? So it says, calculate the magnitude of the linear momentum for the following cases. So it gives us a proton with mass 1.67 times 10 to the negative 27 kilograms, moving with a speed of 5 times 10 to the 6 meters per second. So mass equals 1.67. I'll call this M1. 1.67 times 10 to the negative 27 kilograms. And its speed, V1, is going to be 5 times 10 to the 6. 5 times 10 to the 6 meters per second. Second case, they've got a 15-gram bullet, so mass 2 equals 15 grams, or 0.015 in kilograms. And the speed of this bullet is 300 meters per second, so V2 is 300 meters per second. Third one is a 75 kilogram sprinter running with a speed of 10 meters per second. So M3 is 75 kilograms, and V3 is 10 meters per second. And then we've got the Earth moving with an orbital speed equal to 2.98 times 10 to the 4 meters. So the Earth, our fourth object, is the Earth itself with a mass of about 5.98 times 10 to the 24 kilograms. And moving with a speed of, they said, 2.98 times 10 to the 4 meters per second. All we really have to do is just multiply these. It said compare the magnitudes of the momenta of these 4 objects with no regard for direction. So let's see, without even looking at the calculator, 1.67 times 10 to the negative 27 multiplied by 5 times 10 to the 6, 10 to the 6, and 10 to the negative 27. We're going to get something on the order of 10 to the negative 21, which is pretty small. So despite the proton moving at literally 5 million meters per second, due to its small mass, its momentum is still really small, and actually it's going to be the smallest out of all of these. Then we've got the bullet, 0.015 times 300. It might be comparable to the person running. Yeah, it's kind of close for these, so I might actually have to calculate here. Times 300, so that's going to be 4.5 is what I'm getting for the momentum of the bullet. Oh, then the person wins. 75 times 10 is way more than that. So yeah, the bullet, despite moving at 300 meters per second due to its low mass, still has less momentum than the person. I guess these are already ranked from lowest to highest then. And then the Earth has a lot of mass and a lot of speed. You probably didn't need both, but there's the double whammy. Earth wins by 1.5 miles, or however many meters per second. So this actually allows us to see the units for momentum, which is something I forgot to discuss when writing the equation here. If we're multiplying kilograms by meters per second, then the units of momentum are units of mass times units of speed equals kilograms times meters per second. This is known as a kilogram meter per second. A kilogram meter per second. There is another unit that you could write this as. We will see that in a bit. But before that, let's now talk about change in momentum. Let's talk about change in momentum. I guess I'll do that over here. Change in momentum delta P. Change in, not im, in with an N. I'll just rewrite it. In momentum. So change in momentum we represent with, of course, a delta P, the same way we represent the change in anything, really. Change in a thing is delta that thing. So change in momentum. This is equal to momentum final minus momentum initial, or momentum current minus momentum previous is probably the better way to think about it. And this will be M final, V final, minus M initial, V initial. And usually we will be dealing with objects whose mass doesn't change. We will be dealing with objects where the final mass and the initial mass are the same. In which case, we can just factor out the mass as an M, and that leaves us with V final minus V initial over here. And V final minus V initial, well, we've seen that before. That's what we called delta V. M delta V. So change in momentum, at least in the case where mass is constant. So this is, let me do it in a different color. In the case of constant mass, in the case of constant mass, delta P is equal to M delta V. Now, what would a case with non-constant mass be? Where does that happen? You might remember, I think I mentioned it a little bit when, I forget what the context was. I think there was like a problem that I was working on in one of the previous streams where I was reminded of it. I think I brought up the idea of a rocket ejecting fuel, and what helps the rocket propel itself through outer space isn't just that it's generating some sort of force pushing itself forward, but also what helps it is that it's losing mass, because the fuel that it burns, the mass of that fuel is getting ejected out of the rocket. So in that case, you would actually have a changing mass, although I guess depending on how big the rocket is, you could probably get away with assuming that the mass of ejected fuel is negligible. It really depends on the problem and the numbers you have to work with, but if you wanted to be really precise, you would actually have to factor in the decrease in mass due to fuel being ejected from the rocket. But in most cases, we're just going to be talking about rigid objects. We're going to be talking about things like billiard balls colliding with each other, or blocks hitting each other, or bouncing off of walls, or whatever the case may be. And those objects tend to not change in mass. They don't tend to eject anything or pick up anything. What would be an example of picking up stuff? I suppose like a snowball rolling down a hill, it would be gaining mass as it picks up more and more snow. I guess that would be an example of mass increasing over time. But yeah, that's change in momentum. And the units of change in momentum should still be the same as the units of momentum itself, right? The change in a thing, if you're just doing addition or subtraction between units that are already the same, then you just get the same units. If I add or subtract kilogram meters per second from kilogram meters per second, then I should still get kilogram meters per second. So that's change in momentum. Remember that change in momentum is a vector. A lot of people forget this, so let me give two examples, the easy example and then the not so easy one. And let's see if I have taught you guys well enough to spot the difference before I actually finish answering it in the not so easy case. So let me see which of these problems will be a good example of a simple case. Okay, they don't have anything. I mean, some of them are talking about another concept that I don't want to bring up just yet. So let me just come up with my own. Let's suppose, this is going to be a rather boring example, but let's suppose that we have an object that's moving along with some sort of initial velocity. Let's say the initial velocity is, I don't know, 10 meters per second to the right. And let's suppose this object has a mass of, let's say m is 6 kilograms. And it slides along a surface. Let's say that there's friction on this surface. And sometime later, we see it again, but this time it's moving at velocity v final equals 4 meters per second. What is the change in momentum? Pretty simple, straightforward. Delta P is equal to m delta V is equal to 6 times delta V is V final, 4, minus V initial, 10, is equal to negative 36, right? 6 times negative 6. Negative 36 kilogram meters per second. What does the negative mean? The negative means that momentum was lost. The direction of the momentum change is to the left. Okay, maybe let's modify this example by having again an object. Let's say this time it's also going to be on a rough surface, and let's say it's still 6 kilograms. Let's say it's still 6 kilograms. M is still 6 kilograms. Let me actually draw a dividing line here so this doesn't get mixed up with the stuff above it. And let's say this time there's a spring over here, and it hits the spring, and then the spring pushes it back. And let's say that spring is just up against some sort of wall, like so. And let's suppose in the after image, the object gets pushed back by the spring and gets sent this way. So here's V initial. Let's say it's, I don't know, 8 meters per second. And actually, let's do this. Let's call V initial 10 meters per second again. And let's call this V final, let's call it 4 meters per second again. Now, before you do any calculation, do you think the magnitude of the change in momentum is greater or less than the previous case? That's an interesting question to consider. And can you think of an intuitive reason as to why? Well, let's calculate and see what we get. So if I do my change in momentum formula, delta P equals m delta V, defining right as the positive direction again, I get mass is 6 kilograms times V final is how much? This is something that a lot of students screw up. If we define right as positive, then we, by necessity, are defining left as the negative direction here. So V final is negative 4 meters per second minus V initial is positive 10. Gives us 6 times negative 14, which is, what, negative 84? Negative 84 kilogram meters per second. And of course, the negative just means that the direction of the change in momentum is to the left. So in terms of magnitude, 84 is higher than 36, and significantly so. What gives? I mean, we can see from the math why that's the case, but intuitively, why does this make sense? Because if we understand it intuitively, then we can make sure to always have the right expectations for how big or small the numbers we're going to get are going to be, and that helps us detect mistakes before we commit to them and turn in an exam paper that's going to be graded rather poorly. So in the first case, the object is simply being slowed, but it's not changing direction. It's being slowed, but it's not changing direction. So there's not that much actual change going on. The direction of the change is to the left because if you're reducing a rightward momentum, then it makes sense that you're adding some leftward change to it. Not enough to make it change direction, obviously, but you are adding some leftward momentum to it in order to reduce its speed over here. In the case where you make it reverse direction, well, I kind of just gave it away with my explanation of the first case. Not only are you slowing it down, you have to slow it down from 10 meters per second to not just 4 meters per second. It goes from 10 meters per second to the right to 4 meters per second to the right, and then continues slowing down to 0, and then has to accelerate from 0 to 4 meters per second rather, to the left. Not only does it have to decelerate from 10 to 0, but on top of that you also have to accelerate it from 0 to 4. That's a lot of change. You're not just taking away all of the rightward momentum, but on top of that you're adding a final leftward momentum. So that's a lot of leftward momentum change that's being applied. So there is the reasoning. That is the simple example. Now let's take a look at another example that's a little bit more, well, it's not too hard once you know what to do and what to expect, but the first time students look at it, or if they're looking at it a second time and it's been a while since the first time they saw it, they might make a certain mistake here. Let's say we have an object that collides with a wall. So this object, the way they've drawn it is they've drawn this sort of line of symmetry, and then they've drawn this path. They called this a 60-degree angle, and then they said it basically just reflected at the same angle, reflected at 60 degrees. They said an object with a mass of 3 kilograms, so object, a steel ball, with a mass of 3 kilograms, comes in at a speed of 10 meters per second. And bounces off the wall and is still moving at v final equals 10 meters per second. What is the change in momentum of this object? A lot of people will mistakenly say that the change in momentum is 0 because the mass hasn't changed and the speed hasn't changed. But momentum is a vector. There is a change in direction, so the change in momentum cannot be 0. How do we calculate a change in two vectors? Well, let's draw the components. So V initial is going to have a component upward and a component to the right. So let's see. I guess we're going to take this angle over here, this 30-degree angle. So this over here is also a 30 degrees. And then we're going to do V initial times cosine 30 would be this side, while V initial times sine 30 would be that side. Sine of 30 is 1/2, so V initial being 10 meters per second. V initial sine of 30 is going to be 5 meters per second. And then V initial cosine 30, 10 times cosine 30 is 8.66 is what I'm getting. 8.66 meters per second to the right. Okay. Then we take apart V final. V final which was also 10 meters per second, is also going to be at a 30-degree angle with the horizontal direction, so it's going to have components to the left and up. Its leftward component is touching this 30-degree angle, so that's going to be 10 cosine 30, which we just got as 8.66 meters per second. And its upward component is going to be 10 times sine of 30, which is going to be 5 meters per second. Okay, so if I do V final minus V initial, I can just do it component-wise. V final minus V initial, let's subtract the vertical components first. 5 meters per second up minus 5 meters per second up is 0. What about 8.66 meters per second left minus 8.66 meters per second right? So let's do delta Vy is Vy final minus Vy initial is positive 5 minus positive 5 is 0. And then delta Vx is going to be Vx final minus Vx initial. Let's say that right is the positive direction, so Vx final is going to be negative 8.66 then, since it's to the left, minus Vx initial is positive 8.66, since we've defined right as positive. And now we've got negative 8.66 minus positive 8.66 is, let's see, negative 8.66 minus 8.66. I'm getting negative 17.32. Or what I would prefer to write, just to be on the safer side with whoever's grading my paper, I would just call it 17.32 to the left. (17.32 meters per second of change to the left. So then the actual change in momentum, delta P, is just going to be the mass times that, m times delta V. By the way, in this case, the delta V is just 17.32 in magnitude because delta Vy was 0. If delta Vy was not 0, all you would have to do is take this squared plus this squared and do Pythagorean theorem under the square root. 0 squared plus 17.32 squared, all square rooted, would give you the magnitude of the total change in velocity. I'm sure many of you already knew that, but just in case somebody was confused, because sometimes you forget the things that you should know really well because, you know, you're looking at something new and you're trying to remember things from the past while also trying to absorb the new stuff all at the same time, and sometimes you have brain malfunctions like that, so that's why I mention it. I definitely have my brain malfunction moments. My students are all too familiar with my brain malfunction moments. Anyway, delta P is m delta V, so m was 3 kilograms, so we get 3 kilograms times 17.32 equals 51.96 kilogram meters per second to the left. Or you can keep it negative and indicate somewhere on your diagram that you've decided right is the positive direction. Yeah, there you go. That is a trick question. Do not fall for it. Change in momentum is not change in magnitude of momentum. Momentum is a vector. You don't just subtract the magnitude of the final momentum minus the initial. You don't just do magnitude final minus magnitude initial. You have to take the direction into consideration. It's very, very easy for people to forget this. I always get my students at the end of every year when doing some AP exam review, I always give them this really simple question, and so many of them get it wrong because they're in a rush, they're more concerned with trying to beat the clock than being accurate, and I don't know how many times I've said it on my streams, but accuracy before speed. If you try to do things accurately, speed will come with practice. Speed will come naturally. Do not rush. Rushing leads to really critical mistakes, like the mistakes that students tend to make with this type of question. So, there is momentum and change in momentum covered. Now let's go ahead and look at another concept called impulse. Now let's take a look at another concept called impulse. Impulse we represent with a capital J, and it is defined mathematically as force times change in time. The more force that is acting on an object, and the longer the amount of time that that force is acting on the object, the more impulse that force is said to deliver to the object. So the amount of impulse that a force delivers to an object is proportional to that force and also proportional to the amount of time that that force is being applied. So I guess from the equation we have some sort of rough idea of what impulse is. Its units are going to be force units times time units. So units of impulse are going to be units of force times units of time, or change in time as the case may be, are going to be in newtons times seconds, Newton seconds. So the units of impulse are Newton seconds. But there's more to it than that. There is more to it than that. Because what is a Newton again? If we break down the Newton into more basic units, what is a Newton? Well, we could do net force equals ma, for example. We could take our net force equals ma equation, Newton's second law, and do newtons equals mass is going to be typically in kilograms times acceleration is going to be in meters per second squared. So a Newton is a kilogram meter per second squared. Okay, let's see what happens if we make that substitution. Some of you are ahead of me and already see what that fascinating result is going to be. Kilogram meters per second squared, the newtons, times the seconds. Well, if I multiply by seconds here, and I already have seconds squared in the denominator, that just cancels 1 power of seconds, and I get kilogram meters per second. Oh, wait a minute. Kilogram meters per second, those are the same units as momentum, or also the same units as change in momentum. Is that a coincidence? Of course it's not. We will prove with our equations of kinematics that that's not the case. But it looks like impulse and momentum might be related to each other. Introducing the impulse-momentum theorem. Introducing the impulse momentum theorem. So you might remember from the previous chapter we talked about the work kinetic energy theorem. Here we have something similar, the impulse momentum theorem. Now, the work kinetic energy theorem, I'm just going to rewrite it over here, work kinetic energy theorem, told us what? It told us that the total work done on an object is equal to the change in its kinetic energy. Work total equals change in kinetic energy. So that was our first example of a thing 1 dash thing 2 theorem. Well, now we have another thing 1 and thing 2. So if we follow the pattern, the total of thing 1 equals the change in thing 2. The impulse momentum theorem, the total impulse, J total, the total impulse imparted upon an object is equal to the change in that object's momentum. That's what the impulse momentum theorem states. If you remember your work kinetic energy theorem, then just based off of the similarity of the names, you can very quickly copy down what the impulse momentum theorem is supposed to look like as an equation. Okay, but this is just a statement that we were given. Is there any proof for it? Well, let's derive it. So for the simple case of an object that moves with some sort of initial velocity and has some sort of mass m, and there's some force acting on it. What color do I want for this? Now let's do orange. And let's say there's a force acting on it. The force could be positive or negative. It could be in the same direction or in the opposite direction. I'll say in the opposite direction in this case, but it really doesn't matter. And there's some force, let's call it a constant force. Because if the force is variable, that requires calculus most of the time. So not for Physics 1 students. Physics C students will talk about the variable case when we get to reviewing. So if I have an object, it's got a mass of m, it's moving with some initial velocity v initial, and then there's some force on it. Well, I should say some net force acting on it. So let's assume that this is a frictionless surface, or maybe this force is the friction, and then the other two forces, normal force and gravitational force, cancel out. Then it moves and eventually it ends up with some velocity v final, which I guess in this case would either be a smaller velocity still to the right or some velocity to the left. I'll say smaller velocity to the right, but it really doesn't matter. Okay, so this force must have acted on this mass for some amount of time. Total impulse would just be force times change in time. And if this force is our net force, well, then that's also equal to the mass times the acceleration. So that's ma times delta t. Okay, but a times delta t, assuming this is a constant force, this would then have to be a constant acceleration because the mass isn't changing. So if the force is constant and the mass is constant, the acceleration must also be constant. That means we can use our kinematics equations. What is a delta t? Well, there are many things it could be, but, well, actually, no, not that many things it could be. If we just look at our first kinematics equation, we have v final equals v initial plus a delta t. Oh, would you look at that? And if I subtract V initial on both sides, I get V final minus V initial is equal to A delta T. Okay, so that means I can go M times A delta T. I guess I'll write that on a separate line, equals M times A delta T is V final minus V initial. And V final minus V initial is also M delta V, which for an object of constant mass, I forgot the arrowheads on these, which for an object of constant mass is going to be equal to the change in momentum. So there you go. Total impulse, which I guess is net force times change in time, is equal to change in momentum. You don't just have to take the physicist's word for it. We were able to prove it with previous knowledge. The impulse momentum theorem. Total impulse equals change in momentum. This applies not only to individual objects, but also applies to systems of objects. Which, let me think, do I actually want to discuss that today or save it for collisions? Actually, let me check with the course plan real quick. I'm not sure. We'll see. Let's have a look at some problems, and maybe that'll help me kind of figure out where I want to go with this. Let's go ahead and grab some book problems and see what we can do here. I think it's probably going to be more important to do some pure impulse problems first anyway, because impulse actually helps us explain a lot of things that we apply in daily life when it comes to momentum. Let me look. Okay, here's one that is going to be quite simple, but at least introduces us to thinking about impulse. It says a tennis player receives a shot with the ball, which is 0.06 kilograms, traveling horizontally at 50 meters per second, and returns the shot with the ball traveling horizontally at 40 meters per second in the opposite direction. What is the impulse delivered to the ball by the racket? And the second part is asking, what work does the racket do on the ball? So I guess this is a bit of review of the previous chapter as well. So we have a tennis player holding their tennis racket, their comically large tennis racket, and they receive a ball. There's a ball that comes at them at 50 meters per second, and they hit it and they send it back at 40 meters per second. And they said the mass of the ball is 0.06 kilograms, pretty light, which is what I would expect for a tennis ball. What is the impulse? Questions are, what is the impulse? And what is the work done? What is the work done by the racket on the ball, or by the tennis player on the ball? You could say either way, it's asking for the same thing. Okay, well, we don't know the force and we don't know how much time the racket was pushing against the tennis ball. So we can't calculate impulse directly by simply multiplying force and time. Okay, what do we do next then? Impulse momentum theorem. We can calculate the change in momentum because we know the mass, both initial and final. It's the same thing. The mass of the tennis ball doesn't change. And we know the initial and final velocities. Or at least we will once we define a direction. Very, very important to remember to define a positive direction every time you do one of these linear momentum problems. It's something that a lot of students forget. You have to remember to define a positive direction because these aren't just 50 and 40. One of these is going to be a negative while the other is going to be a positive, and which one it is really depends on your personal preference. At the end of the problem, I would recommend just reporting magnitudes, and if there's a need to report direction, report it in words, kind of like what I did back up here. Come to think of it, I forgot to circle this result. Anyway, so for the sake of convenience, I want my change in momentum to be positive, so I'm going to make my final velocity positive, which means my initial is going to be negative. So I'm going to say right is positive here and left is negative. So I'm going to call this the negative 50. Okay, we can do m delta v. Fortunately, they're both velocities along the x direction, along the horizontal direction, so I don't really have to do any trig or Pythagorean theorem or any of that stuff. I can just do direct addition and subtraction. We get 0.06 times v final is positive 40 minus v initial is negative 50. So that's 0.06 times 90. So that's the same as 0.6 times 9, which is 5.4 kilogram meters per second, or Newton seconds, as we discussed earlier. Newton seconds and kilogram meters per second are the same thing. I imagine a lot of people will lean towards Newton seconds because it's less writing, which I suppose is fine, but do remember both forms because you will see sometimes multiple choice questions on the AP exam that will ask you about stuff like that. They'll give you something in one set of units and then all the answer choices will be the same thing expressed in different units and only one of them will actually be correct. So part A is done. The impulse is 5.4 kilogram meters per second, or Newton seconds. And it's to the right, if you wanted to specify direction, to the right. Is that visible on screen? Yes, it is. And then the second question was, what's the total work being done? How much work does the tennis player do? Well, we don't know the force and we don't know the displacement through which the racket was pushed. Oh no, what are we gonna do? Pretty much the same thing we just did for calculating the impulse, really. If we can't calculate directly using force and displacement, then we can calculate indirectly using the work kinetic energy theorem. Total work equals change in kinetic energy. We do know the mass, and we do know the initial and final speed. We can calculate change in kinetic energy. So work is equal to change in kinetic energy is equal to 1/2 m times 50 squared or negative 50 squared, it doesn't really matter. Once you square it, the negative disappears, minus, oh, wait, no, that's the initial, sorry. That's going to be 40, final is 40, minus 1/2 m times v initial. This is the 50 squared. And so 1/2 m, 1/2 of 0.06 can be factored out as a 0.03. And then 40 squared minus 50 squared, 1600 minus 2500. That's going to be 900. So 0.03 times 900. The 100 and the 0.03 simplify to a 3, and then 3 times 9, that's going to be 27 joules, negative 27 joules. Which is to say that more work is done on the racket, actually. Work is done on the racket because the ball came with more kinetic energy, so some of that kinetic energy was transferred to the racket, sending the ball back with less energy than it had to begin with. So yeah, the work was done on the racket, not by it. That's what the negative sign is telling us here. And I suppose if we did have some information about the amount of time it took to whack the ball and send it back, it's probably going to be on the order of milliseconds. But if we had that information, we could then calculate the amount of force in that racket swing. And usually the follow-up question that you would see in a physics textbook for something like this is they would tell you, like, you know, they would, at least conceptually, they would ask you, you know, does this cause concern, the number that you get? And the answer would probably be yes, because yeah, playing too much tennis, your wrists have to withstand a considerable amount of force, and you know, if you're just playing casually from time to time, it's okay, but if you're not wearing protective equipment and being really careful with how much you're playing tennis and how you hit the ball with the racket and stuff like that, if you're not taking those extra precautions, then you can do some serious damage to your wrists. So that's, I guess, the mini health warning / lesson of the day. Okay, let's have a look and see what else we can find in here. Is there... No, the backside of that is already used. Let's grab a new sheet. And let's see what more we can do with impulse and momentum. Okay, here's one about a football player. So it says a 0.5 kilogram football is thrown toward the east with a speed of 15 meters per second. 0.5 kilogram football. That's American football for those of you watching from outside of the United States. This thing, 0.5 kilograms in mass, is thrown toward the east with a speed of 15 meters per second. A stationary receiver catches the ball and brings it to rest in 0.02 seconds. So a receiver over here catches it and brings it to rest, V final equals 0, in an amount of time, delta t equals 0.02 seconds. Part A, what is the impulse delivered to the ball as it is caught? And part B, what is the average force exerted on the receiver? The average force exerted on the receiver is also the average force exerted on the ball. Newton's third law, action and reaction. Whatever force is exerted on the receiver who's stopping the ball is also the amount of force that they exerted on the ball to stop it. That's just Newton's third law at play. Let's use this color. Is our lighting looking okay? I mean, it is earlier in the day, so we have a lot of natural sunlight, but I'll have to remember to check for that and flip the lights on when and if it's needed. So, impulse delivered to the ball. Let's see. Well, we can't calculate it directly because we don't know the force yet. That's actually the second question. So instead of calculating it as force times change in time, we can calculate it as change in momentum. So we can just go momentum final, which is, well, it's brought to rest, so 0, minus momentum initial. Actually, I'm just going to focus on magnitude here so that I don't have to keep re-explaining my negative signs. 0 minus, what was the momentum initial? Well, it would have been 0.5 kilograms times V initial is 15. So 0.5 times 15 is 7.5, or negative 7.5, the absolute value of which is 7.5. So 7.5 kilogram meters per second, or Newton seconds. Okay, that's part A. So I guess I'll circle it. And then part B was asking, what is the average force? We have no reason to assume that this football player applied a constant force while bringing the ball to rest. In real life, humans aren't really all that good at applying constant forces, after all. Maybe if it was a machine or some sort of mechanism. But we can just do, now that we know what the total impulse is, we can just say it's equal to average force times change in time, magnitude of the average force times change in time. So that's going to be 7.5 equals, we don't know what that force is yet, times change in time is 0.02 seconds, divide by 0.02 on both sides, which is essentially just multiplying by 50. Either way, 7.5 divided by 0.02 gives me 375. I get 375 newtons equals the magnitude of the average force. Enough force to lift 37 kilograms. That's a pretty decent amount of force, actually. Especially when you consider that it was a 0.5 kilogram football to begin with. It needed to be stopped with a force that would have been enough to lift something, exceeding 70 times its weight. Right, is my math right here? 37.5 over 0.5. Yeah, in fact, about 75 times its weight on the dot. Okay, now then, what other examples can we look at? I do want to, now that we've talked about average force, I do want to talk about some variable force situations that we can deal with in AP Physics 1 that don't require calculus. So let's have a look at one of those, or two. Here's one. It says the force shown in the force versus time diagram in the figure acts on a 1.5 kilogram object. Find the impulse of the force and find the final velocity of the object if it is initially at rest, and find the final velocity of the object if it is initially moving along the x-axis with a velocity of -2 meters per second. And after this, I need to remember to comment a little bit on momentum and impulse on graphs. At least impulse is going to be covered in this problem, but there's also a kind of graph from which you can derive momentum. So the graph they have looks like this. They have a 1 here and a 2 here, and this is force along the x direction in units of newtons. And then over here they have, on the horizontal axis, time in seconds. And it goes 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. And they've drawn a graph where the force is a constant 2 up until 3 seconds. Up until 3 seconds, let me use a different color for this. Up until the 3-second mark, the force is a constant 2 newtons. And then after that, it linearly decreases to 0 by the time 5 seconds have passed. With a graph like this, we can actually figure things out without the need for calculus. So let's go ahead and reread the questions it was asking. So it says the force shown in the diagram is acting on a 1.5 kilogram object. So that's the first thing to note. Mass of the object is 1.5 kilograms. And it wants us to find the impulse of the force. It wants us to find what's the total impulse, at least its magnitude. Usually when you're asked to find impulse and momentum, they typically just want the magnitude in most cases, but if you want to play it safe and include a direction as well, you're more than welcome to. In this case, the positive direction is whatever the positive x direction is, since they mentioned this is a force acting on the object in an x direction. And because we know this force is positive throughout, positive up until it's 0, and the force is never in a negative direction, so we have no reason to assume there's going to be any negative momentum changes, any negative impulses. Direction of impulse should just be the direction of the force, which is also the direction of the change in momentum. So that was the first thing they wanted. What's the total impulse? What is the final velocity of the object if initially at rest? V final if V initial equals 0. And again, V final if V initial is equal to -2 along the x-axis. Okay, so many of you can probably already guess what we need to do in a situation like this. We've seen this in, let's see, we've seen it before in kinematics, where we were deriving the equations of kinematics from graphs, and we saw it pretty recently with the work chapter, work done by a variable force. And now we see this again. It's just going to be area under the curve. If we had a constant force, if we had a graph where it was just a constant force, so just a straight horizontal line multiplied by some amount of change in time, then the impulse would just be whatever this height is, I guess we'll call it f0, multiplied by whatever this time is, I guess we'll call it t0, would equal the area of this rectangle. It has a height of f0 and a width of t0. f0 times t0, the impulse would simply just be the area in this case. So same idea over here. If you chop this up into little slices, into little rectangles, then you're going to get the height of the rectangle in units of newtons and the width of each rectangle in the units of seconds. And if you calculate the areas of those rectangles, they will be in units of newton seconds. So area under the curve for a force versus time graph gives you impulse. Total impulse then for this is going to be height is 2 times width is 3. So over here we get 6 Newton seconds for the, I guess it looks like a square, but it's supposed to be a rectangle. And then for this triangle, we've got 1/2 base times height. So base from 3 to 5, the base is 2, so 1/2 of 2 times the height is 2, so 1/2 of 2 is 1, times 2 is 2. So that's going to be 2 Newton seconds worth of area inside that triangle part. So the total impulse must then be 6 plus 2, J total must have a magnitude of 8 Newton seconds from the area under the curve of that graph. Second part, what is V final if V initial is 0? Well, the total impulse is also equal to the change in momentum. And all I have to do is just add the change in momentum to the initial momentum to calculate the final momentum. If change in momentum is equal to momentum final minus momentum initial, then add momentum initial to both sides and you get momentum initial plus change in momentum equals momentum final. And this is the part where we need to know the mass. So momentum initial, 1.5 times, well, I guess we don't need it for part B yet, but we will need it for part C. 1.5 times magnitude of velocity initial was 0, plus a change in momentum of 8 is equal to momentum final. So the final momentum must be 8 kilogram meters per second. Or Newton seconds, whatever you prefer. Okay, so that is in the second case. So I guess I'll call these parts A, B, and C. And this is specifically for part B over here. For part C, it's 1.5 times, let's see, the initial momentum in part C, V initial is negative 2 meters per second. So they've already decided what the negative direction is for me in this problem. Plus 8, this 8 Newton seconds, like I said earlier, is going to be in the positive direction here because I got my area from multiplying a positive force by a positive time. If this graph continued and it continued like this over here, and I had to calculate the area of this triangle below the time axis, then that would be some negative impulse that I would have to subtract from the total. And if there was more area under the time axis than above, then overall I would say that my impulse is negative. But that wasn't the case for this problem. Anyway, 1.5 times negative 2, that's going to be negative 3. So momentum final is negative 3 plus 8 is positive 5 kilogram meters per second. I can already feel myself falling asleep. Maybe streaming today was not the best idea after all. I'm probably going to catch a mistake or two when looking at this video. Surprisingly, when reviewing all of these stream videos so far, I haven't caught any mistakes, and I'm going to take that as a sign that I haven't made any fatal mistakes that I didn't actually catch in the video before ending it. Of course, it could also just be a sign that I'm really bad at checking my own work. But if it's gonna happen, then today would probably be a good day for it to happen. So far, I'm not seeing anything too wrong with my math, but there's a good chance that I might catch myself wording things in a confusing way. Can't wait to see what it'll be like reviewing the footage for this stream. That's all I'm saying. Okay, so with that problem out of the way, there was one other thing I wanted to mention regarding graphs. What was it? Oh, right. So another kind of graph you might encounter in this chapter. Now, what color do I want to use here? I guess we haven't really used this one much today. So the other kind of graph that you might encounter is a momentum versus time graph. You could have an object whose momentum is graphed on the vertical axis and time is graphed on the horizontal axis, and maybe it looks something like this and zigs and zags, or maybe it's some sort of smooth curve, which would probably require calculus, or at least just drawing a tangent line and eyeballing it. That is something that they might ask you to do in AP Physics 1. They might give you like a curved graph, and although you can't exactly calculate slope, they might ask you to find, some instantaneous value, and you would just have to draw. They would have like some grid marks already on the page for you to draw, and then use those grid marks as a guide. It would already be, divide it into a bunch of squares like this for you. And you would use that to just give an approximate slope. And of course, as long as it's within some sort of reasonable range, you would get credit. But outside of those curved graphs, which are usually more reserved for the calculus-based students in AP Physics C, you can take a momentum versus time graph and use its slope to derive a certain quantity. If we rearrange some of the equations we saw earlier, then you might be able to deduce what it is. We said that impulse is equal to change in momentum, right? That's the impulse momentum theorem. Impulse equals change in momentum, but we also defined impulse as force times change in time. Force times change in time equals change in momentum. So then, if I simply divide change in momentum by change in time, I can get force is equal to change in momentum over change in time. Oh, what's that? P final minus P initial over T final minus T initial. Delta P over delta T, kind of like delta Y over delta X. It's a slope formula. So yeah, on a momentum versus time graph, slope equals force. On a momentum versus time graph, slope equals force. Over here, momentum is increasing, so there must be some positive force, and you see a positive slope along with that. Over here, momentum is not changing, so there mustn't be any force accelerating or decelerating the object. Over here, we have some sort of positive force. Here we have no force. And then over here, momentum is decreasing, which means there must be some negative force. There must be some force opposing the direction of the object's momentum and slowing it down. So yeah, on a momentum versus time graph, if you can calculate the slope, that will be equal to the force. If it's a more curved graph like this, then you would actually get the instantaneous force as opposed to just some sort of constant force that's applied for whatever interval your straight segments span. Apart from that, I feel like there was one more thing I was forgetting. Oh, right, average force. So if we go back to this over here, so I calculated the total impulse here as 8 Newton seconds. If I wanted to then go back and figure out what's the average force that's being exerted, kind of like the question with the football earlier, then what I could do is I could take my 8 Newton seconds, I could do total impulse equals average force, force average, or I guess force bar is what I called it earlier. Both notations are the same thing, times change in time. The change in time overall is 5 seconds, so if I have 8 Newton seconds of impulse over the course of 5 seconds, then 8 over 5, that's going to be 1.6. The average force is going to be 1.6 newtons. So replace this graph with, I'll use a darker color. If we replace this graph with, let's see, so that's going to be 1.2, 1.4, 1.6, 1.8. So 1.6, somewhere around here. If I replaced this graph with a simple straight horizontal line graph that looked like this, then the area of this new rectangle, this single rectangle, would be equal to the area under the pink stuff that I had in the beginning. So I guess what I'm trying to say here is if you're trying to find the average value of something and that thing goes up and down on a graph, then all you have to do is calculate the total area and then divide by the length of the interval. And then whatever number you get from that, that is the height of the horizontal line that you have to draw in order to get a rectangle with an equivalent area. Those of you doing calculus by this point in the school year should have already encountered that average value of a function. So for you guys, that's a reminder, but for the algebra-based students, actually, I think I talked about this before. I don't quite remember, but if I didn't before, now you know. To find the average value of a function, calculate the area under the curve of that function and then divide by the full length of the interval. And there you go. I think I want to do one more example here with impulse, one more practical application that is explained by impulse, and then we can talk about conservation of momentum and we'll talk about conservation of momentum, compare it and contrast it with conservation of energy, and then I guess I will touch a little bit on collisions, but save most of the collision stuff for next stream. Yeah, I think that's what I'm going to do for the rest of the day. And who knows, I might actually finish earlier than 3 hours this time. For your sake, I hope that is the case. Because you're about to be hit with a double stream if everything goes according to schedule. I should be back tomorrow. So next question says, the front 1.2 meters of a 1,400 kilogram car is designed as a crumple zone. So here we have a car, and then its front parts over here, the front 1.2 meters of it is designed as a crumple zone. Let's write that out. Crumple zone. Oh goodness, I spelled it wrong already. Crumple zone. Cars are designed so that when they run into other cars or concrete or whatever, or a tree, they are designed to have their fronts and backs smushed. That is on purpose. We could definitely make the front and back ends of our vehicles out of rubber that is more resilient, and then we don't have to, spend a lot of money on expensive car repairs and car parts whenever an accident occurs. However, there is a physics-based reason why we don't do that, why we don't use rubber to design the front and back ends of our vehicles. We want our vehicles to crumple. So let's go ahead and work this problem, and then we'll discuss this after seeing the numbers we get. So the front 1.2 meters of a 1,400 kilogram car, mass equals 1,400 kilograms, is designed as a crumple zone that collapses to absorb the shock of a collision. If a car traveling 25 meters per second stops uniformly in 1.2 meters, how long does the collision last? What is the magnitude of the average force on the car? And what is the acceleration of the car? Express the acceleration as a multiple of the acceleration of gravity. So if a car traveling 25 meters per second, V initial equals 25 meters per second, stops uniformly in 1.2 meters, so that's going to be our delta x is 1.2 meters, that's the crumple zone. How long does the collision last? Part A. What is delta t? Part B. What is the magnitude of the average force on the car? So magnitude of, I'll call it F average here because I don't think I have enough space for the bar to be really visible on top of the F. And then for part C, what is the acceleration of the car? In multiples of g is what they say. Express this in multiples of g, or in other words, in g forces, if you remember back when I first mentioned that. They want us to compare this to the acceleration due to gravity. Okay. We can just use plain old kinematics for part A. Uh-oh. I got it. We can just use good old kinematics for part A. So we have delta x, we have V initial, and we said the car is brought to a stop, so we know V final is 0. The car is brought to rest in 1.2 meters. So that's 3 kinematic values. We can use them to calculate the other 2. Come to think of it, we can answer parts A and C just with kinematics alone. So which kinematics equation would I use if I have V initial, V final, and delta x? I guess I would actually start with the third equation, solve for the acceleration, and then use that to solve for delta t. Yeah. I suppose I actually have to solve for acceleration first. So V final squared equals V initial squared plus 2a delta x. 0 squared equals 25 squared plus 2 times the acceleration times 1.2. Or rather, it would have to be negative 1.2 because if V initial is 25 meters per second forward, then no, it's not negative. It would be positive. The car would be moving forward 1.2 meters, or at least the driver's seat would move forward 1.2 meters before coming to a stop, by which point all 1.2 meters of crumple zone is gone. And then that would have the acceleration come out negative, which makes sense because from moving to the right to not moving, acceleration would have to be to the left. Okay. So that's where that negative I was seeing is going to come from. So subtract 25 squared on both sides, we get negative 625 equals 2 times 1.2 is 2.4a. And then negative 625 divided by 2.4 is negative 260.416 repeating. So I'm just going to do negative 260.417. Acceleration is negative 260.416 0.417 meters per second squared. If I go ahead and use that to calculate delta t, I think I want to use the first equation for that part. So let's switch to another color. V final equals V initial plus acceleration times time, or delta time, whatever you want to call it. V final is 0, V initial is 25, acceleration is negative 260.417, and time we don't know yet. Add 260.417 t to both sides and divide. 25 divided by 260.417 is about 0.096. 0.095 and then a bunch of nines. I'm going to say 0.096. So delta t is about 0.096 seconds. Really fast collision. So this is like a car bumping into another car, or a concrete wall, or a tree, or something of that sort. Really fast, not even a full tenth of a second. Okay, now part B wants us to calculate how much force is in this collision. What's the average force that would be exerted on the car in this case? We can just use the change in momentum and link that to impulse. Basically, we're just going to use this over here. And I might as well use all this extra space I have up here. So let's see, F average equals, actually, let's use this rearranged version, is equal to delta P over delta T. Now we just want the magnitude of it, so we'll take the absolute value on both sides. So it's going to be equal to, let's see, magnitude of the change in momentum would be, magnitude of final momentum is 0 minus initial momentum is 25 meters per second times 1400. So minus 1400 times 25 over delta t is 0.096. Okay, so that's going to be 0 minus all that. You're just going to get a negative, and the absolute value bars will kill that negative. So it's just 1400 times 25 is 35,000 divided by 0.096 is an even bigger number. I'm getting force average, its magnitude, is about 364,583 newtons. .33 repeating if you want decimals in that. And then finally, what is the acceleration in multiples of g? Well, we already got the acceleration before. It was 260.417. So we're going to do 260.417 divided by g is 9.8. So that gives me 26.57. So the acceleration is equal to 26.57 g. About 26.5 times the free fall acceleration. And this is a good thing, this amount of force and acceleration are good. You can probably survive this. What you can't survive, however, is if the car's crumple zone, if the car's bumpers were made of rubber. If the car's bumpers were made of rubber, then what would happen in a collision with another car or a tree or a wall is, one, it would be brought to rest in a shorter distance because the rubber would just kind of compress a little, but not by very much. Do I have something that I could use here to illustrate this visually? I don't know if I have any good rubber objects I could use, but let me look around real quick and see something I can squeeze that can just bounce back after I'm done squishing it. Let me think. I suppose this little foam cup holder will have to do. It's not exactly rubber, but I think it helps to illustrate the point. So if we pretend this is like the front end of a car made of rubber and it collides with something, it might get compressed a little, but not by very much. Like if I try to pinch it, you see I can't really completely flatten it, right? It compresses by a tiny bit and then just stretches back out. So imagine something similar happening, but with rubber, which is an even tougher material than this. So it's gonna, if it was solid rubber, it would compress even less than this. So you get that really tiny amount of compression. You get that you get a really tiny displacement, nowhere near 1.2 meters. We're talking like maybe a couple centimeters at best. And imagine how much higher the acceleration would have to be then, because our acceleration is going to be negative 625 divided by 2 times whatever the compression distance is. So divided by a much smaller compression distance, you would get a much higher acceleration. And with a higher acceleration is a higher force, which you're not very likely to survive. But it gets even worse than that, because rubber has another property, in that if the car was made of rubber and ran into a wall, chances are it wouldn't just stop at the wall. Rubber has a tendency to bounce, and you might remember back where we did, let me see, where was it? You might remember back over here when we compared the same object going from 10 meters per second to 4 meters per second in the same direction versus going from 10 to 4 being bounced back. We said that the object that has to reverse direction requires a greater change in momentum, and therefore requires a greater impulse, and therefore requires a greater amount of force. And all of that is really, really bad news for the driver. If you made the bumpers of a car out of rubber, the car would be safe, but the driver would probably be dead a couple hundred times over. So that is why cars, by design, are meant to crumple if their front or rear ends collide with something at high speeds. That's also the idea behind airbags. So airbags, crumple zones, all sorts of safety features like that. The whole point of them is that they give you this extended compression distance, which reduces the amount of acceleration and therefore the amount of force in a collision. And not only that, but also by extending the compression distance, the added benefit is not only a lower acceleration, but also a higher time. lower acceleration and higher time. That increase in the time it takes for the collision to happen, if you increase the denominator over here, what does that do? It reduces the force in the collision. So there's just some practical applications to impulse and momentum for you. Now let's go ahead and talk about conservation of momentum and its conditions. Well, really, it only has one condition. When we talked about conservation of mechanical energy, we said that it was associated with what? Mathematically, we said that mechanical energy was conserved if it wasn't changing. That's what we meant. Did I write conservation? Oh, conservation of. This is how you know my brain isn't working at full power today. Conservation of mechanical. Wow, my brain is really malfunctioning today. Conservation of momentum. Hey, at least I'm catching them before the end of the stream, so I don't have to write some sort of pinned comment full of corrections, or even worse, just take down the video and re-record. At least it's not that bad. Conservation of momentum. So, let me think. What was I saying as I was writing this? That's probably what confused me. I was talking about conservation of mechanical energy. We said that mechanical energy was conserved whenever, mathematically, it meant that the change in mechanical energy is zero. And the change in mechanical energy, we said, was also equal to the non-conservative work. So mechanical energy was conserved whenever its change was zero, which implies then that it's conserved whenever the non-conservative work is zero. Something similar applies to momentum. So when is the change in momentum zero? Momentum is conserved when the change in momentum is equal to zero. And we just talked about something that's directly linked to change in momentum. If change in momentum is equal to total impulse, then when change in momentum is zero, that implies that the total impulse must also be zero. And this tells us that the net force times time must be zero. And time being zero is not really that interesting. Of course, momentum isn't going to change when time is frozen. That's not a very interesting observation. The more interesting thing is this net force being zero. So when the net force on an object is equal to zero, that is when momentum is conserved. Well, kind of. So this is true for a single object, but what about multiple objects? What about multiple objects? We already looked at an example with conservation of mechanical energy across multiple objects. We did the problem that had the 3 blocks linked to each other through ropes over pulleys, and we added the non-conservative work for each of them, and the total non-conservative work was zero, even though it wasn't zero for any of the individual blocks. Kind of the same idea here. If we have more than one object, so this is for a single object. If we have multiple objects, then if we treat those objects as a system, then we would add each of their net forces, net force on object 1 plus net force on object 2 plus net force on object 3, and so on, and that would have to be equal to 0. So this is for multiple objects. This is for a system of objects that are being treated together. This is going to be the more interesting thing. This is going to involve collisions, usually between two objects. Sometimes, to make it more fun, we'll add a third or maybe even a fourth object. But usually, we're going to use this for collisions involving two objects. So for multiple objects, the sums of the net forces need to be 0. But if those objects are mostly exerting forces against each other, you might remember what happens to the forces they exert on each other. If I have, for example, let's say 3 blocks, and let's say they have different masses. This will be M3, this will be M2, this will be M1, and let's say there's some sort of applied force over here. And let's say we have a rough surface, so each of them has friction acting on it. So there's force friction 3. We'll say it's kinetic friction. And here's force friction 2. And here's force friction 1. And then we have, let's see, what else? We've got force of gravity and normal force. Those are going to cancel each other out. But I'll draw them anyway. Force gravity 3, force gravity 2, force gravity 1. I don't know why I drew that one longer. And then normal force 1, normal force 2, and normal force 3. And then, of course, we've got the tension forces. And then we've got the tension forces. I guess we'll call this force tension 1, and this will be force tension 1, and this will be force tension 2, not drawn to scale, and this will also be force of tension 2. And if we were to do all the math and write out the net force equations for each of these, what would we get? Vertical forces are all just going to sum to 0, so I'll skip on that. But net force 1 in the x direction equals m1 times a of the system equals, let's see, I'm going to use right as positive, so that would be tension 1 minus force of friction 1. And then for the second object, net force on object 2 in the x direction is going to be m2 times the acceleration of the system equals forces to the right, that's tension 2, minus forces to the left, that's tension 1 and friction 2. And then for the third object, net force on object 3 is equal to m3 times the acceleration of the system equals force applied to the right minus force of tension 2 to the left, and also minus force of friction 3 to the left. If I were to add net force 1 and net force 2 and net force 3, you remember what happens. the tension forces disappear. They cancel each other out. So if I do net force 1 plus net force 2 plus net force 3, that equals m1 plus m2 plus m3 times the acceleration of the system, equals the tensions cancel out, and I'm left with my positive force is the force applied. That stays. And the friction forces stay. Minus force of friction 1, and minus force of friction 2, and minus force of friction 3. And I believe, if I recall correctly, I pointed out when doing these problems that the forces that disappear when you add the net forces of multiple connected objects, the forces that disappear are all forces that the objects exert on each other. In this case, through the rope, yes, but they're exerted by the objects themselves tensing up that rope. So these are forces. This tension force 1 is the tension force that M2 exerts on M1 through the rope, and then this wait, did I call it tension force 2? Tension force 1, rather. But you get what I'm saying. This force of tension 1 is the force that M1 exerts on M2. So these tension forces are exerted by one object within the system on another object within the system. And I believe, if memory serves, that I referred to such forces as internal forces. Internal forces. In case I didn't mention them before, let's give a little definition here. Forces that are exerted by parts of a system on other parts of the same system, on other parts of the same system. Now, because these forces obey Newton's third law, these forces are going to be equal in magnitude and opposite in direction. They don't immediately result in a net force of 0, not for the individual objects, but when you put the objects together as part of a system, well, now you're making it so that if I'm putting M1 and M2 and treating them as a single system, well, now this action-reaction pair acts on, I guess you could say, the combined M1 plus M2 object. So when the two forces are now on the same object, all of a sudden they can add, or in this case subtract with each other and cancel out. So internal forces, as a consequence of them being action-reaction pairs, they will always cancel each other out when the two objects they affect are part of the same system. So these internal forces, they always disappear. And what's left is, well, everything else. These are external forces. These are what we would call external forces. Forces from outside of the system. Forces exerted by, well, in the applied force case, by the person or machine that decided to pull on block 3. The friction forces applied by the ground or floor, whatever this surface is that the blocks are on, which I'm not considering as part of my system. These are called external forces. So the internal forces, whenever you add the net forces of multiple objects, those are always going to go to 0. That's just a given. So The real requirement here that I'm looking for, if the internal forces are automatically going to go to zero, then what I actually have to check in a system of objects is whether or not the external forces go to zero. So you will see this condition stated more explicitly in textbooks as net force external must equal zero. This is the condition for conservation of momentum. The net external force on a system of objects must be zero in order for momentum to be conserved within that system. The individual objects within that system might have their momentum change, but the total across all the objects within that system, that total will stay the same. As long as net force external is equal to zero. A lot of people forget this condition. A lot of people will just look at a problem, and I've even heard some people unironically say momentum is always conserved. That is not true. There is a little bit of like hand-wavy logic that we use, and I will use this too, to justify doing certain calculations, to justify assuming conservation of momentum at least on a temporary basis in order to do a calculation, and then after a collision is done happening, we can then, I guess, unsuspend the net external force if it isn't zero. We'll talk about that more once we get to it, probably tomorrow. But for now, the condition is that the net force external needs to be zero in order for there to be no change in momentum across a system of objects. Now, this is not the same condition as the condition for conservation of energy, which is why I want to emphasize, why I want to compare and contrast the two things, because a lot of students will assume that conservation of energy implies conservation of momentum or vice versa. It's not true. It's not true. So I'm going to do momentum conserved momentum not conserved, and then over here I'm going to have mechanical energy. I'll just abbreviate it as ME. Mechanical energy conserved and mechanical energy not conserved. Four situations. All four of these situations are possible. You can have situations where mechanical energy is conserved and momentum is conserved. You can have situations where mechanical energy is not conserved while momentum is. You can have situations where mechanical energy is conserved but momentum is not. And you can have situations where neither mechanical energy nor momentum are conserved. All four of those scenarios are possible, so make sure you check both conditions. Make sure you determine whether or not the net force external is zero, and determine whether the work non-conservative is zero. Those are the only way to tell when momentum is or is not conserved and when energy is or is not conserved. If you determine one is conserved, that doesn't tell you anything about the other. And if you determine that one of them is not conserved, that still doesn't tell you anything about the other one. So let me see if I can give some examples here. I don't know if they'll make a lot of sense since we're probably not going to dig into collisions that much today, but I'll write them down anyway. So a condition under which mechanical energy and momentum are both conserved. This is what we will call elastic collision. And we will dig deeper into that later on. Let me check with the time. We might be able to dig into this towards the end today. But if not, then we'll see it tomorrow. Situations where mechanical energy is not conserved while momentum is, well, that would be what we call inelastic collision. And I guess I can at the very least tell you what the scenario would look like for each of these. So an example of elastic collision would be just two billiard balls colliding and bouncing off of each other. And let's assume that they roll on like a smooth, frictionless pool table. That would be an example where both mechanical energy and momentum are conserved. Or if you've seen that toy, the Newton's Cradle, the one that looks like a mini swing set with the little metallic balls. It's called a Newton's Cradle. You can look it up. That would probably be faster than looking at my illustration. A Newton's Cradle would be a pretty good example of elastic collision. Of course, in the real world, air resistance will eventually slow down the Newton's Cradle, but ignoring air resistance for the first few minutes of the motion of a Newton's Cradle, you can say that those collisions are approximately elastic. In elastic collision, think of something like, say, two cars crash into each other and they break in such a way that their crumpled parts all kind of fuse together. And then whoever is bringing the tow truck has to figure out a way to pull the cars apart or make sure to tie them so that they can pull the cars together, one or the other. That would be an example of an inelastic collision where the momentum is conserved, but the mechanical energy is not, because the mechanical energy is lost in the form of heat and friction as the metal of the two colliding cars starts to fuse. And it's also lost in just the deformation, the crumpling of the bumpers of the cars. So that's an example where mechanical energy is not conserved while momentum is. Momentum not conserved while mechanical energy is. This one is actually really simple. A ball in free fall due to gravity. Mechanical energy is conserved here because gravity is a conservative force. No non-conservative work is being done, assuming, of course, we neglect air resistance. But the momentum is not conserved because, well, whatever initial velocity this ball has, it's going to change as it accelerates while going down due to the influence of gravity. So, really, really simple example of mechanical energy being conserved while momentum is not. And then, what's an example where neither mechanical energy nor momentum are conserved? I guess we could just do the same thing, but this time with air resistance involved. A ball falling while there's some force of some drag force, some air resistance force. Or I guess another thing you could have is a ball just rolling on a rough surface. The friction takes away mechanical energy and it takes away momentum. Those are two pretty simple examples where neither momentum nor mechanical energy are conserved. So the main takeaway is that these two types of conservation are completely independent of each other. One can happen without the other, and vice versa. You can have both, you can have neither. You can have the first one and not the second one, or the second one and not the first one. You need to check these two completely separate conditions to figure out which of these four scenarios you are looking at. Now then, I guess we can talk about elastic collisions, and then that is what we will wrap up with for today. Tomorrow we'll dig into collisions a little bit more. For now, we'll just talk about collisions in one dimension between two objects. So if we assume we're working with two objects, actually I want to start a new sheet for this. If we are talking about two objects, let's say I have two blocks on a smooth surface colliding with each other. The collision could happen in a number of ways. It could be a collision where both objects are approaching each other directly. One is moving to the right, the other one is moving towards it to the left. Or it could just be the case that one object is moving to the right faster than another object. So I guess that would be V1 initial, and this would be V2 initial. And V2 initial is smaller than V1 initial, so object 1, M1, catches up to M2 and bumps into it at some point. That's one way it could happen, or the other way that your mind probably goes to is V2 initial being to the left. Either scenario still has the possibility of what we call elastic collision, which just by definition is a collision in which both momentum and mechanical energy are conserved. That's just the definition of an elastic collision. Oh, and by the way, since the word inelastic sounds a lot like anelastic, I will try to emphasize the vowel sound when I'm talking about anelastic collision versus inelastic collision. If you say it really fast, it's really easy to confuse people. So I will try to emphasize the vowel sound. I will try to slow down and emphasize it whenever I'm talking about anelastic collision versus inelastic collision. And I would recommend that you practice the same, especially if you're working with a study group, because communicating clearly is what makes or breaks a study group. Anyway, where was I? Elastic collisions. So elastic collisions, by definition, are collisions in which mechanical energy is conserved. Usually, you're going to be working on a level surface. There are no changes in height, so you don't have to worry about potential energy. And usually there won't be springs involved, so you don't have to worry about elastic potential energy either, neither gravitational nor elastic. So the only mechanical energy left to consider is kinetic energy. So this will be on a smooth surface, no friction. There's a normal force upward on each object that is completely countered by the gravitational force. So no net force external. The only other force that's going to be exerted on these objects will be the forces they exert on each other when they collide. But if we treat these two objects as part of a system, if we do net force 1 plus net force 2, those internal forces are going to disappear. The net external force, the normal forces and the gravitational forces, they cancel out. So net external force is 0 here. Net force external, we can easily see why this would be 0 for two objects running along a smooth surface. Okay, what about non-conservative work? What about non-conservative work? Well, the non-conservative forces, in this case, would be the normal force, which does no work because it's perpendicular to the displacement of each object, and the forces that the two objects exert on each other. But those internal forces, whatever work object 1 does on object 2, and equal and opposite work is done by object 2 on object 1, because they're going to be equal and opposite forces, and the two objects are going to be moving through the same displacement during the time that they are exerting those forces on each other. So very much like the example that we did, again, with the, well, not this one. Let me see if I can actually find it in one of our recent sheets. I might have to check both sides. Where? Oh, here it is. Yeah. Very much like this problem that we did, I don't know if it was one stream ago or 2 streams ago. Very much the same way that the non-conservative work due to the tensions canceled out between these objects back when we did this energy problem, the same idea applies here. Whatever force, I guess it would be called a normal force, that these two objects apply to each other when they actually make contact. Whatever work one of them does on the other, an equal and opposite amount is done by the second one on the first. So the total non-conservative work across both blocks will be 0. And so we have both conservation of momentum and conservation of energy. Okay, conservation of energy, we can write it out. That's going to be potential energy gravitational, well, that's 0, plus potential energy elastic, that's also 0, plus kinetic energy will be kinetic energy of object 1 initial plus kinetic energy of object 2 initial plus the non-conservative work, which of course is 0, equals no gravitational or elastic potential energy final, and then you're going to have a kinetic energy 1 final and a kinetic energy 2 final. So this just simplifies to 1/2 m1 v1 initial squared plus 1/2 m2 v2 initial squared equals kinetic energy 1 final is 1/2 m1 v1 final squared plus kinetic energy 2 final is 1/2 m2 v2 final squared. And we can cancel the 1/2 everywhere. We don't need that fraction. Just this is good enough. So that's the energy condition. What about conservation of momentum? So if net force external is equal to 0, then the change in momentum is 0. Specifically, the change in momentum of the system is 0. That means change in momentum of object 1 plus change in momentum of object 2 is 0. I guess I don't need that other equal sign since I have the 0 there. Okay, that means then that 0 is equal to change in momentum of object 1, that's m1 v1 final minus m1 v1 initial. Mass of object 1 times its final velocity minus the mass of object 1 times its initial velocity. Plus, I guess I'll write it down here for space. Same thing for object 2, m2 v2 final minus m2 v2 initial. Now, of course, if this was a two-dimensional situation, we would actually want to separate delta P1 and delta P2 into x and y components. So the way I would do that, we'll talk about it more next time, but basically I would just do delta P system x equals 0 equals delta P1 x plus delta P2 x, and just basically write it out over here, just putting an x in the subscript for each of these wherever you want to put it, and then do the same thing with y delta P system. Y equals 0 equals delta P1 y plus delta P2 y, and you can just do conservation of momentum for the x direction and the y direction separately. In fact, you might have two-dimensional problems where the momentum is conserved, say, in the x direction but not in the y, or vice versa. So that's the other benefit of being able to separate the two, is that sometimes one of them is conserved and not the other, so you can at least work with the one that is conserved. Well, I mean, if you have enough information, you should be able to work with any situation, whether the momentum is conserved or not. Kind of like what we did with mechanical energy, where I kept on emphasizing, as long as you know what the non-conservative work is, it doesn't matter whether the mechanical energy is conserved or not. Kind of same idea here. But anyway, hold on to this thought for next time. We'll play around with this some more next time. I want to go back to this. I want to go back to assuming this is all happening in one dimension. How do I want to rewrite this? I want to take these negative terms and move them over to the left. So that's going to be m1 v1 initial and m2 v2 initial. I'm going to move those to the left, and what I'm going to end up with is m1 v1 initial plus m2 v2 initial. This and this got added to the left, equals m1 v1 final and m2 v2 final stayed on the right. Okay, and let me actually rewrite that kinetic energy one just to make it a little bit cleaner. So that's m1 v1 initial squared plus m2 v2 initial squared equals m1 v1 final squared plus m2 v2 final squared. Now, you will probably be faced, for elastic collision situations specifically, you will probably be faced at one point or another with a situation where you know the initial velocity of object 1 and the initial velocity of object 2 and both masses, but you don't know either of the final velocities. You have two unknowns. And in that situation, where you have two unknowns, you guessed it, you need two equations. This is why you would actually need both the momentum and energy equations. But working with the energy equation where one of your unknowns is squared and having to potentially solve quadratics is not fun. So we can actually derive a third equation that is much easier to use so that we don't have to use this one anymore. This one, not fun. So we can actually combine these two equations to come up with something that is easier to work with. And if you guys paid attention during, what was it, the second stream, I believe, might have been where I did it, there was actually a problem way back then. Oh yeah, we're going to look back at the math essentials. Hold on. Let me open up the math essentials and let me show you this, and you tell me if you see something that looks awfully familiar from Unit 0. Let me switch screens here. Okay, let me scroll down to it. It was under Problem 2. Tell me whether or not this over here, let me zoom it in. Tell me whether or not this is looking awfully familiar now. Something squared, thing 1, thing 2 squared plus thing 3, thing 4 squared equals thing 1, thing 5 squared plus thing 3, thing 6 squared. And then notice the second equation is basically the same thing, except the squares are gone. Is it looking familiar? The H is basically the M1, the G is the M2, the M is V1 initial, the N is V2 initial, the P is V1 final, and the Q is V2 final. There you go. I already solved it for you way back then. So go back to, I forget if I solved it in the stream itself or if it was in one of the videos linked in the stream, but it was either the very first or the very second stream of this course. So your homework is to try and simplify this. Your homework is to try and simplify this, and you should get something. You might not get exactly this result, but you'll get something that can be rearranged into this result. You should be able to get the following. You should be able to get something like this. V1 initial minus V2 initial equals the negative of V1 final minus V2 final. You should be able to get something that looks like this or can be rearranged into this. You might get it in a different form, so if I distribute the negative sign, let's see, you might get something like this instead. That's going to be negative V1 final and positive V2 final, so you might get something that looks like this. Or you might even, I'll add these to the opposite sides. I'll move this here and move this here. You might get something that looks like this, V1 initial plus V1 final equals V2 final plus V2 initial. You might get something like that instead. But whatever you get, I would prefer that you take the extra steps to convert it to this form. because there's actually an intuitive meaning for this result, which we will discuss next time. So, deriving this from these is your homework. Once you've derived this, anytime you need to solve for two unknown final velocities, you can just use this equation together with this, and you won't have to deal with quadratics anymore. It might take a lot of effort to prove this, but it is very much worth it because this equation is linear. It's much better to use this with our first equation rather than using kinetic energy with our first equation. So there you go. That is homework, and for other homework, let me think. I guess if we look through, let me look through the book and see what kinds of problems they have. So that's chapter 8, sections 8.1 through 8.6. I mean, I don't know if you'll have enough time to do the homework considering the next stream is scheduled for tomorrow, but hey, you don't have to watch it tomorrow. You can give yourself a few days and then watch the next episode. Let me see. So I guess we covered 8.1 and 8.2 for the most part, and I guess we touched on 8.3. So maybe the conceptual questions under 8.1 through 8.3 and let me actually show you what I'm seeing on screen. So yeah, in our course book under chapter 8, conceptual questions, maybe try the conceptual questions under 8.1 and 8.2, and I think with what we've covered you might be able to do some of 8.3. And then for the problems and exercises, you should be able to do everything under 8.1 and 8.2 now, and maybe a little bit of 8.3. Maybe a little bit, but we haven't really done any calculation yet with conservation of momentum, so I wouldn't blame you for holding off on that. See if you can find a couple of easy ones here and try them out just to sort of preview for next time. And I think that will be it for today. So, any other announcements before I wrap things up? So, tomorrow's collisions, we're going to look at these one-dimensional collisions. We're going to do some problems with those. We're also going to look at some two-dimensional collisions, and then that will be the chapter. Oh, and we'll do kind of mixed momentum and energy problems. So there are going to be problems where we have to use both momentum and energy to solve. And sometimes we might also have to do some projectile motion and kinematics along with it. So that'll be fun, watching it all come together. But otherwise, that should be the end of this chapter, just done in 2 streams. We will still see bits and pieces of momentum in future chapters every now and then. So this isn't like some sort of throwaway chapter. The reason we went through it so quickly isn't because it doesn't matter. It's because we've been learning carefully about force and energy and kinematics all this time. And now all that time and effort we've put into that is paying off, or at least hopefully it is for you if you actually did put in the work and really made sure to master those previous topics. So yeah, this is going to be a rather quick chapter, and after next stream we will be hopping straight into circular motion and gravitation. So look forward to that. That is it from me for today. Hope you had fun and learned something useful. I am all tuckered out and I need to rejuvenate before next stream. Take care. Class dismissed.